Welcome to this biomechanics video where we talk about motion capture and filtering the data that you collect during motion capture. Here's an example of position versus time data that you might collect. And we've talked in previous videos about taking position data and turning it into velocity data and acceleration data via differentiation. So when we take that position data and we differentiate it numerically, we get something that looks like this. You can see a pattern. It's reasonable. When you differentiate again to get acceleration, it starts to look really, really noisy. There's still a pattern here that you can see, but it's getting difficult, and it's getting difficult to interpret that meaningfully. And the reason for that is every time you divide by a really small number, you amplify any noise that's present in your signal. So noise is just that extra stuff on your signal. There's frequently 60 hertz noise from the power lines as part of the environment when we collect data, because here in North America we use 60 hertz. In Europe, where they use 50 hertz, it's 50 hertz data, or 50 hertz noise. The greatest sources of noise, though, in an experiment like this where we're collecting motion data come from the fact that we're interested in measuring the motion of the skeleton. But what we're actually measuring is the motion of the soft tissue surrounding the skeleton. Technically very difficult and not particularly appealing to participate in a study wherein one measures the motion of the skeleton directly. So because the markers are attached to the soft tissue, any motion in that soft tissue, from floor impacts, from muscle contractions, etc., creates noise on your signal. Fortunately, this is often at a higher frequency than the skeletal motion that we're interested in. So we can take advantage of that using a technique called filtering. So before we jump into filtering, let's talk just for a minute about frequency components. In math class, you might remember something from math class called a Fourier series, where you talked about all of these different frequency sine waves and adding them together. If you take these three sine waves and combine them, you end up with this pretty complicated looking signal. If we could go backwards, start with the complicated signal, and deconstruct the sine waves, we could use that information to cut out the sine waves that we don't want, the ones with high frequencies that are due to soft tissue noise. So using a mathematical technique called the Fourier transform, we can do exactly that. We can take a signal that's in the time domain that looks like the yellow signal we were just looking at, decompose it mathematically into the sine waves that make it up, and then look at the frequencies of those sine waves and how much of each of those is present in the signal in the frequency domain. Computationally, we use something called the fast Fourier transform, which is just a way of saying that we do the Fourier transform math quickly using the computer to take a time domain signal and turn it into a frequency domain signal, which might look something like the figure on the right here, where you have the signal portion there on the left and then noise. You'll note that there is some overlap, but mostly the noise is separate from the signal. We can then take something called a filter and allow the part we want to pass through and cut out the part we don't want. So on the left is a high pass filter, which allows through high frequencies. On the right is a low pass filter, which allows through low frequencies. The cutoff frequency determines where that transition point is. And you'll notice that the filters aren't perfect. This high pass filter will still let some lower frequencies through. This low pass filter will still let some higher frequencies through. But mostly you get the stuff that's on the desired side of the cutoff frequency. So here's that signal we were looking at a minute ago with a filter applied to it. And you can see our signal is still pretty much the same, but the noise part of it has been dramatically reduced. And we've picked a cutoff frequency that corresponds to this point kind of right here, so that hopefully we're removing the noise and not removing any of the signal. Now in reality, we've probably removed some of the signal, but we're willing to make that trade-off to get rid of the noise to make analysis easier. So here's the data that we were looking at. High pass or low pass filter, which one? And why? You're going to use a low pass filter because we want to get rid of the high frequency noise. And you can see here the 12 hertz cutoff frequency. Our X data, our position data on the left still looks about the same. Our velocity data in the center is a little bit cleaner, but then the acceleration data, we start to see a really big payoff where we get a much smoother, much clearer signal than what we got originally. So there are some different kinds of filters. The two most common that are used in biomechanics are the Chebyshev filter and the Butterworth filter. The Chebyshev filter is this one with it's called a ripple in the passband. The passband is the frequencies that get passed. So the Chebyshev filter has a ripple in the passband, which makes it less desirable. The Butterworth filter is smooth in the passband, but starts to drop off in its gain here in the at the upper frequencies, getting close to the cutoff frequency. The Chebyshev filter does actually fall off closer. It's closer in its fall off to an ideal filter, which is this dotted line here. So there's trade-offs to make, right? Do you want to amplify your signal a little bit weirdly with something like the Chebyshev and then really cut out the undesired frequencies up here? Or do you want to make the trade-off near the cutoff frequency of decreasing the gain, right? So you've got to make some choices. More commonly in biomechanics, Butterworth filter is used, but both Chebyshev and Butterworth are used, so it's worth knowing the differences between the two of them. Similarly, or in addition, a filter has an order number, so that's the number of components. If you're talking about an analog filter, that's literally the numbers of capacitors and inductors that you're using to build the filter, the order. In a digital filter, it's what mimics, or what number of components is being mimicked in the digital math that we're using to apply the filter. We're using digital filtering in this class. So a first order filter, you can see has a very low slope up here in the cutting off region, the region where it clips the signal, but it has a really slow roll off out here in the undesired frequencies. A 10th order filter has some more distortion here at the edges, but it's also computationally very expensive digitally, or component-wise very expensive in the analog filtering world. Typically in biomechanics, we're somewhere between a second order and a fourth order, probably really more frequently in a third to fourth order Butterworth filter. So you'll be experimenting with doing those in MATLAB. We're going to be using the filtFilt command to filter our data. The filtFilt command, as opposed to the filter command in MATLAB, has 0 phase shift. So what I mean by phase shift is when you filter the data, you slide it horizontally, and the filtFilt command filters it one way to slide it, and then filters it back the other way to slide it back. So you can see here the original waveform, the filtFilt command in the blue here, and the filter command in the orange. So the filtFilt forward and back filtering results in a signal that's in phase with the original, or a filtered signal that's in phase with the original signal. You're going to be using the butter command to set your filter coefficients. So the butter command is where you determine the coefficients that go into the filtFilt command. That's where you're telling it that you're using where you're setting up that you're using a Butterworth filter, that you're using a fourth order filter, that your cutoff frequency is 10 hertz. Those kinds of things you specify in the butter command, and then put those coefficients that you get out into the filtFilt command. Note that you do need to normalize the cutoff frequency when you use the Butterworth filter. So your cutoff frequency divided by half times your sample rate. So you're adjusting for how you're sampling. And as always, remember to check the help documentation. These are new commands. You haven't seen them before. Go figure out how they work by reading the help documentation. Bring your questions to class. I'll see you there.